Thank you very much, and thank you for the invitation. And being the last speaker, I should thank the organizers who've organized a fantastic conference, Akshay, Erez, and Yanis, under very difficult circumstances with the weather. Amazingly, we are only 5 minutes late on the last lecture, so let's thank them for a fantastic. So I will talk about something much more basic. We'll just be in the upper half plane. We won't leave the upper half plane. So I'm willing to use anything from anywhere else to understand the upper half plane. So if it means going to another group, this is still my interest. So I'm going to talk about the nodal domains. I'll show you pictures in a second. And if you like, just think of the full modular surface, level 1, everywhere unramified Maass cusp forms. Now these are very transcendental objects. They are objects, they're the even eigenfunctions. They are the objects, by the way, that Selberg invented the trace formula to produce these objects. Maass and Siegel had been studying theta lifts, and they had the dual pair SOPQ lifting to SL2, that particular dual pair. Siegel had lifted 1, and Maass understood you could lift any form, and he defined a Maass form for that purpose. And his experience with holomorphic forms is you're supposed to land up with a Eisenstein series plus a cusp form, but he couldn't construct any cusp forms. He asked Siegel, who was his advisor, and the two of them tried to understand, are there any cusp forms, especially even cusp forms like this. And Selberg went away, thought about it, knew some spectral theory, understood if you compute the trace, maybe you could prove a Weyl law. And that's then the trace formula was born in the non-compact case first, precisely for this purpose, to produce these guys. So these are everywhere unramified forms. They're very transcendental. And they're more important to me than the holomorphic forms because they control other things. So these are the ones we'll be interested in. So they're even. They could be odd also, but let's make them even. So there's a reflective symmetry that's a non-holomorphic symmetry of the modular surface. So holomorphic forms don't see the symmetry, but Maass forms do. So I'll be even. And one can also think purely in terms of vibrating drums here, because the even ones are going to have Neumann boundary conditions on the half of the fundamental domain of the modular group. And my question is, or the question is about the zero set of an eigenfunction. It's called the nodal domain. So let me remind you the definition. The zero set is where phi is real valued, and the set where phi is 0 is called the nodal set, and the complement x minus the zero set breaks up into components, and those components are called nodal domains in a vibrating drum. And the question I want to address, and I've always wanted to address, are how many of them? So there's a simple upper bound that is due to Courant, which in the case of a compact Riemannian manifold is very clean. It just says the number of nodal domains. I'm going to show you a picture in a second. The number of nodal domains of the nth eigenfunction. This is just a simple variational characterization, minimax. It's in Courant-Hilbert. The nth eigenfunction has at most n nodal domains. So the number of nodal domains is bounded by n. This can be improved, the constant in front of n. It was done by Pleyel. And remarkably, Bergan was able to, after like 100 years, improve that in the 6th decimal place recently. Slightly improved constant in the upper bound for the number of nodal domains in any dimension. Okay, so there's an upper bound, but a lower bound is very difficult. This is a present that Hedgehog gave to Selberg. Selberg constructed these, and Hedgehog computed these numerically in the 70s. And this is the nodal set of the biggest eigenvalue I know of a cusp form, even cusp form. It's got eigenvalue lambda, which is roughly 125 squared. I colored in the zero set for you so that you can see where it's positive and where it's negative. Otherwise, you just see this weird nodal line. And there are various, these are the nodal domains. There's another nodal domain. There may be some big ones. And you can see there are quite a few of them. For some therapeutic reasons, I colored it in other colors with a crayon. It was very pleasurable. Pink are what I'm going to call inert. Green are what I'm going to call split. And that's because there's a symmetry, that symmetry which is z goes to minus z bar. And a nodal domain is either invariant under that symmetry, in which case it's inert, or it's split. The green ones are split, and they're fewer in number in this picture, and the pink and the other ones are inert. So I was very proud of this. The work I'll be talking about here is joint with Amit Ghosh and Andrei Reznikov, who might be here. Yeah, there he is.
Sorry, what is the color coding?
The color coding is the green are the split ones, and the others, just to change to make the colors, are inert. So it happens they're more inert ones, but that's, you'll be fooled by that. I was very proud of this. I sent it to Ghosh, and he said, and he, of course, the background is due to Hedgehog. He says there's a command called paint, which does much better than your coloring. I said, come on, man, I spent 3 hours and I feel real good. Okay, I can't argue that that looks prettier. Anyway, how many nodal domains there are, and that's what this lecture is about. Since seeing these, I've always wanted to say something, and it's a very difficult problem. Ghosh and I studied holomorphic forms and zeros of holomorphic forms on the real axis for the full level, and obtained some results there, and it inspired this. Just to convince you, this is 1925. This is in Courant Hilbert's book. It is not the case that the number of nodal domains needs to grow with the eigenvalue. And in fact, it's very hard to see how to make nodal domains. That's part of what I want to explain here. Anyway, the first example, Courant was impressed with his upper bound, and he was hoping maybe that, or wondered, I guess, if there's a lower bound. And you can just take a flat torus where the eigenfunctions are just products of sines and cosines, and you can make arbitrary large you can make eigenfunctions with arbitrary large eigenvalues for which there are only two nodal domains, as you can see in this picture. I'll return to this picture. There's something that's, I mean, you can see it beautifully fits into this jigsaw puzzle with just two nodal domains. And there's nothing preventing that. And you can do this on a sphere as well. This was done by Hans Levy. You see, it's very difficult to look here and decide about the topology of your nodal domain by just doing a local analysis. And in this, in an analytic study of anything, you usually can study things locally, but it's much harder to study them globally. And that's what is the difficulty in producing nodal domains. Yeah.
Why do you study nodal domains as opposed, for example, to level sets?
You mean the nodal domain is, for an eigenfunction, something very special in that it's where the eigenfunction, if you solve a wave equation, doesn't move. So I could show you Kaladny pictures and things, but in the terms of eigenfunctions, very natural. In real algebraic geometry, which is very close to this, asking about the topology of the zero set of a polynomial, homogeneous polynomial, the real set, you could ask why zero? And there's a fundamental difference. It's projective. You want to define things projectively, singles out zero. And it is the most interesting level set, and you will see something. I will address something towards that in another setting, in a random setting. But in terms of eigenfunctions, it's a natural set, and it's like the zeros of a polynomial, of a real polynomial. All right, the problem's so difficult that at the time that Hedgehog produced those, we didn't say anything, we just looked at the pictures. However, along came physicist Michael Berry, who made a very interesting suggestion, which of course is a suggestion and no more than a suggestion, but it's very compelling. And that is, if you have a classically chaotic system, and you quantize it, whatever that means, I'll translate that in our example now in a second, and you quantize it, then the eigenfunctions of the quantized system should obey like random monochromatic waves, which I'm going to define for you now. And that's a question in probability theory. My experience in number theory is when you have a question in probability theory, once you've understood that that's your question, the probability theory is supposed to be trivial. In other words, every probabilist knows how to do it. That's a central limit theorem, that's random matrix theory, that's that. This is a case where probabilists have no idea what's going on. And so I got sucked into this to try to understand this problem for the last 8 years, as you'll see. Just what the random answer should be. What is chaotic? Well, the classical mechanics here is the geodesic motion on the unit tangent space to this modular surface, or more generally hyperbolic surface. The unit tangent space is essentially the group divided by gamma, and that is well known to be chaotic. That's a theorem of Hopf, whatever chaotic means. So whatever Berry has in mind, it better apply here if he thinks it applies in general. And so let me tell you what a random monochromatic wave is, because at least I'll then be able to tell you what the answer is supposed to be for the modular surface, and then I'll tell you, then I'll get into what we can prove. So to define a monochromatic wave, you can do this in any dimension. Let me take the two-sphere, and let me look at the eigenfunctions on the two-sphere, which are just spherical harmonics or harmonic polynomials of degree k in R3, and restrict them to the sphere. The dimension is 2k plus 1, as everybody knows. And these are, when restricted to the sphere, are eigenfunctions of the round sphere with eigenvalue basically k squared. And to make a random function, I take a linear combination. So all these guys have the same eigenvalue. They're 2k plus 1 of them. I take a linear combination of these functions with coefficients aj, which are chosen independently, identically distributed with mean 0. So the mean 0 here will eventually translate to something about the 0 level. And variance 1, that's a normalization, doesn't matter what you choose, but the key is mean 0. Makes 0 a very special level set. All right, and if I take the random function here, means I choose these a's at random, and of course k is going to go to infinity, then you could ask what the eigenfunctions look like. And Berry would say that in your chaotic system, in the modular surface, or in even in higher rank, especially negatively curved manifolds, you should expect the individual eigenfunctions to behave like these random things, and we should be able to answer the question for random at least, but that doesn't mean it's easy. And it took quite a while till anybody was able to say anything interesting, and there's a beautiful theorem of Nazarov and Soden from 2008, which addresses how many nodal domains does a random spherical harmonic have. When I say random, I mean you choose it. When k goes to infinity, every choice you make will have this number. The random, there's concentration around the mean. Everybody will behave this way. It's not an average over the ensemble. It's an individual random statement. There is a constant. That's their theorem. This constant's quite mysterious. The only thing they know about it is positive, such that the number of nodal domains for the eigenvalue lambda, remember Courant's upper bound is basically a constant times lambda. If I normalize the area to be 1, it's lambda. And they're saying there's another constant, which clearly must be less than Courant's constant, such that the random guy is going to have that many nodal domains. In other words, the random monochromatic wave wants to have many nodal domains, some fraction of the maximum that it can have. You could ask more generally, how many nodal domains are there? Every nodal domain is a planar domain. It's got some topology, some connectivity, and you could ask how many nodal domains are simply connected, how many are doubly connected, how many are triply connected. So here's a picture that you see in many conferences due to Barnett, who's kind of the king of computing. This is a random monochromatic wave. So that's really what the random guy looks like compared to Hedgeholl's modular eigenfunction. Actually, when you compare, which I'll show you in a minute, what you get for the random and what Hedgeholl's thing is, everything fits perfectly as far as the statistic goes. Anyway, that's a picture which is really illustrates what a random monochromatic wave of degree 80 looks like. Let me repeat, if he does these experiments, each time he does it, the picture is identical. It's not the same set, but the structure of the picture is the same, the count's the same.
What is alpha?
Alpha is part of a theory of, I'm about to tell you, it's in this paper of Wiggin myself. It just is saying it's spherical harmonics rather than random real algebraic geometry. So there's a extension of Soden and Nazarov's work that Kanzani, Wigman, and I have developed over about 4 or 5 years. We finished it basically last year in any dimension. Anyway, it says there's a probability measure, a universal probability measure on the integers, on the connectivity types, such that the number, if you take a random spherical harmonic or random monochromatic wave, the number of nodal domains of connectivity 1 will be mu of 1, that fraction of the total number, So there's a probability measure. That is, a probability measure is highly non-trivial. And the theorem that we prove, again, is that this is positive for every m. We don't give any explicit lower bound for any m. The numbers are absolutely tiny, even for the total number. So if you take, there have been numerical Monte Carlo experiments by Nastăsescu, Conrad, and mainly Barnett, which show in the kind of picture you saw a moment ago, actually deliver for you what this measure is, because each time you run it, you get the same answer. And one finds that the Soden-Nazarov constant is about 1 in 20. So it's about 1/20th of Courant's upper bound, that a random monochromatic wave, that's how many nodal domains it'll have. If you actually make rigorous the proof by Soden and Nazarov, which is quite involved, it was done by Ducosy Island, here you get the 10 to the minus 70 as the lower bound. The truth is 1 in 20. In other words, the proof is quite crude, and it's even that it's positive is quite a miracle in the proof. I don't want to go into it. There are a number of variants on it.
Is this something in the arithmetic setting, or do you have
No. This is all random. Okay. I'm just telling you now what I'm expecting the answer to be. And I detoured for a number of years just to understand the random case, and this in probability theory is not known, and requires new methods introduced first. The main technique is used with Soden and Nazarov.
And this is for dimension 2?
This is for dimension 2.
But manifold is anything, the metric or...
Now, these are universal, that's true. But I'll say a word about higher dimensions, because it's got a very serious meaning in this random world.
What do you mean by universal?
Universal means it doesn't depend on the manifold.
But depend on distribution.
No, the distribution's universal. You take any manifold, you take band-limited functions which are monochromatic, you always get the same answer. These are actually universal distributions for this monochromatic wave that will come from any setting in which you can define it. Let me repeat, that's one of the reasons I colored that in. It was more recent. I checked, then I did the count in Hedgehold's picture against these predictions, and they're quite accurate. And these are the even guys, and there's Eisenstein series which move things a little bit in Weil's law, so it's quite impressive actually. I want to make this remark about higher dimensions because there's something that I never expected, but in the last year has become clear, that when you go to higher dimensions, all the theorems we prove can be proved. That is, the number of nodal domains will grow like the maximum according to Courant's upper bound of n. If you're the nth eigenfunction, then the random monochromatic wave will have a constant times n nodal domains in any dimension. That constant will depend on dimension. But that constant that you get there is so small that when, even in dimension 3, when Barnett experiments with this, he never sees anything but 2 nodal domains. So in this world, that constant seems to be about 10 to the minus 15 in dimension 3. In reality, in proof, it's 10 to the minus worse than what Island got. So for practical purposes, in dimension 3 and higher, you probably never see more than 2 nodal domains in this world if you are a random eigenfunction. It may explain why it's so damn hard to make a nodal domain. So the lower bound is very hard. And how do we produce? I should say, where in the random do you produce a nodal domain? So this is the proof. This was done by Soden and Nazarov on the sphere. Let me just say, in the random case, you find an unusual event and show that event happens a positive proportion of the time, but it's not so unusual. But in higher dimensions, this event is still positive proportion, but I'm saying extremely rare. And then there's an ergodic theorem which says if something happens, it must happen again and again and again. So you construct this by hand and show that certain random configurations allow it. It's not something that I could do in the modular group. Okay, so that's the background, and the prediction now is clear, and it seems to work perfectly. If you take an eigenfunction, one of these Maass forms, and you take a high frequency, it seems to have many nodal domains. I will return to the inert and split ones in a second, because they are kind of important. All right, so I want to tell you what we can prove. So what can we do here? So the first thing, I will explain that the techniques that go into this proof use many of the tools that have been discussed. various period formulae, sub-convexity bounds, QUE, all these tools which were not available many years ago actually are used here. So the first theorem is you take the modular group itself. It's conditional. I'm going to assume the Lindelof hypothesis for the L functions of these everywhere in ramified forms are standard L functions for GL2 for cusp forms. I assume the Lindelof hypothesis for those who aren't inclined that way. You could say I'm assuming the Riemann hypothesis, so you know I'm assuming something that's true, even if I have no idea how to prove it. And in that case, Gauss, Reznikov, and I are able to give a lower bound of the number of nodal domains, which is a power lambda to the 1/24. As I go into the proof here, you'll understand there's a limit to how much this method could ever give. More generally, if you give me any congruent surface whatsoever, so this is a surface here would mean a Riemann surface or a complex curve, but since I'm doing hyperbolic geometry and with a Riemannian metric, I call it a surface. So it's either a congruent subgroup of SL2Z, or it's a congruent subgroup of corresponding to a Shimura curve, a division algebra of a certain type, which at the real place would give you a discrete, an arithmetic subgroup in SL2R. In any of those cases, there's a similar theorem. So I assume that the condition I need to produce, there's going to be a technique to produce nodal domains. I'm going to assume that my surface carries a reflection symmetry, just like it did in the modular surface. So there should be a reflection symmetry from the surface to itself. I'll let delta be the fixed point set of that symmetry. That will now it's easy to show that's a union of closed geodesics. And those will be this will be tori, in which I'll do an integral later. It's a finite union of closed geodesics, actually disjoint. And I'll assume all the Maass forms are also I've been diagonalized also with respect to this symmetry. In other words, they're either even or odd. I don't care. Think of them as being even. In general, there may be some Hecker operators that don't commute with this, but most of them will, so that's not an issue. The tools that will be used here don't require that you be a Hecker operator of every eigenfunction, every Hecker operator. You don't need your eigenfunction to be an eigenfunction of every Hecker operator, just almost every, all but finitely many. All right, so under that condition, we have a theorem, which is the same theorem. It's slightly weaker. Assume Lindelof. This time I'm assuming it for GL2, for automorphic L functions, for number fields F, which are defining the quaternion algebra. Then we have a slightly worse result, but still a power. There are many nodal domains. And that, I view as an achievement. We are able to show that the number of nodal domains goes to infinity with a power. A beautiful recent result, and that I want to end up explaining this result, of Zhang and Jung, proves an unconditional result. Those two results were conditional. Using that technique, but shortcutting it brilliantly at the end, they prove a completely unconditional result. Let X be compact as any of the examples you've seen so far. Then they prove that the number of nodal domains goes to infinity with lambda. And that's unconditional, and I think a remarkable achievement, and it just appeared in JAMS. This is remarkable because it's difficult to make nodal domains, and they're showing that the number of nodal domains goes to infinity. Even though the number of nodal domains is supposed to be a tremendously large number, when you see the technique, you'll see that one's only making, by this whole method, very special kinds of nodal domains. In particular, and this to me is the most attractive of all of them, if you take an arithmetic triangle group, of which there are 84, this theorem compact would be the nicest ones, it applies to that. So if you take this triangle group here, which has got angles pi over 6, pi over 6, pi over 2, which is an arithmetic triangle group, and you just solve the Laplace phi plus lambda phi equals 0 with Neumann boundary conditions. That's even eigenfunction. And that's arithmetic, so it also can be assumed to be a Hecker eigenform. So you have Neumann boundary conditions, you have a triangle. This is a theorem about a vibrating triangle in the hyperbolic plane. There are 84 of them for which we understand this theorem. The theorem is that the number of nodal domains will go to infinity with lambda, unconditionally. That's their theorem. So if you want to get rid of all the automorphic forms, of course the proof uses all the automorphic forms. If you want to get rid of it, you can talk about a hyperbolic triangle vibrating, and it's got number of nodal domains goes to infinity. So I repeat, if we went to a higher dimensional hyperbolic space, or maybe even a higher rank symmetric space, I make one nodal domain, never mind anything else. Well, there are always two at least.
But you expect to, according to the things that you said.
No, I expect that in the world we live in, you'll only see two if you ever did an experiment. I'm sure that there will be, the Berry conjecture will be true, and we have proved there are many of them. Just the constants in the proof in dimension 3 are so small. I should have said where that came from. I didn't explain that. I do understand now. The reason there are only two domains in this real world once you get to 3 dimensions, apparently from the numerics and from some heuristic considerations, is that we are in a supercritical regime. That is, there is a nodal domain which occupies almost the whole space. There's this massive guy which eats everybody up. There are little pieces left over which are the ones which are growing with a constant times lambda. This is in the random model. Let me clarify, in the random model. And this is not proved in 3 dimensions, even in the random. This is remaining, and one of the most interesting remaining issues is this percolating component. So there's apparently, once you get to dimension 3, in dimension 2 we are at critical percolation, dimension 3 we seem to be supercritical, and in the supercritical regime there is always this massive guy eating everybody up. So this component everybody wants to join to it, and then there are just 2 components numerically. And he doesn't see numerically any little guys, which are the random construction is based on finding little guys. All right, now we can't do this in the arithmetic situation, so I want to describe the tool. So the proofs of those 3 theorems that are described all use what are now bread and butter tools in the study of automorphic forms which vary in the level, not here the level is fixed, or vary in the eigenvalue and vary in the weight. Those are problems that we've been studying, or many people have been studying for years now, and that's the kind of tools that go in, and let me remind you of 3 of them, and these are all used critically. So the first is the quantum unique ergodicity theorem of Lindenstrauss and Sandararajan added escape of mass property, but this is basically due to Elon, which uses measure rigidity tools from quite different sources. And it says the following: suppose I'm on one of my x gammas, I don't have to assume here that phi lambda is even around the fixed set of that stabilizer, just phi lambda is any guy. Hecker eigen, L2 norm 1. If I take a function A, which is a smooth function or continuous function in L2, well, let's say smooth function on SL2R over gamma, let's say it's compact quotient. I take a function A, you can use A, which is a function on the unit tangent space, to create a pseudo-differential operator of order 0 called op A. And op A phi lambda is the matrix coefficient that is defined by op A. So if A were just multiplication, if the function A only didn't depend on k, so if I had it divided by k then was invariant, this would be just multiplication by A of x, and it would be measuring phi lambda squared as a probability measure. How does it distribute as lambda goes to infinity? But this has got a further feature to what's called the microlocal lift of this, so it's got much more information in it. And the quantum unique ergodicity conjecture, which was proved by Lindenstrauss, asserts that this converges to the integral of A. So that's a statement about how the mass of phi lambda moves around in the 3-dimensional space. And we want to try use that to make nodal sets. The second theorem that we'll be using is a non-trivial upper bound for the L infinity norm. So there's an old result of Ivanets and myself that the L infinity norm in these arithmetic situations of any eigenfunction, which is a Hecker eigenfunction, is at most, I want you to look at the exponent there. There are times when exponents are important. The trivial bound there is 1/4, and the most important thing is this is less than 1/4, and that will be used critically later. So that's a definition of a subconvex bound. It means a bound better than the local bound. And the particularly pleasant problems are those where this is enough to get something. Of course, people have criticized some parts of this kind of subject of being gymnastics of people improving exponents. That's important, but it's really important when that exponent makes a difference between having zero and before you start, and having something after you start.
So the 1/4, is that something you said?
1/4 is a completely general bound due to Abramovich and Hormanda in any Riemannian surface, the L infinity bound is at most lambda to.
Works whether you're not compact or not.
Okay, the general statement will never be for a non-compact situation because people don't know what the boundary looks like. So all the Riemannian thing will be for compact or with some standard type of infinity like a cusp. Then it will work the same way. It's actually incorrect that the L infinity norm is bounded nicely when you go into the cusp. So there's a bit of a danger there. An actual blunder in this paper has a mistake in it. I've openly admitted it in a commentary on this paper. So there's a statement there that is made for the non-compact situation, which is easily fixed up, but just not true way up into the cusp. So there's a subtle point there. Now that I'm aware of that point, we'll avoid it, and everybody has since. We need this for a general Shimura curve. Then the bound, for some reason, I think this is just a hiccup, is still better than a quarter. It's not as good as the bound we have. The methods are similar, but there's some technical reasons they got something slightly weaker, but I'll be using it. I haven't quite understood why they got something weaker. Okay, so that's a non-trivial upper bound for the L infinity norm. And of course, there's a formula here that, as I always joke with Jean-Luc, that his formula actually is an amazing formula because L functions, we know exactly what their size is on the critical line if we know the Riemann hypothesis. So it tells us what the ultimate truth of the size of a number is. So if you're interested in the size of a period, so this is Wolfsburger's period formula, we'll be integrating phi along this closed geodesic. In this arithmetic case, phi will be even in the application. Omega will be a character of the torus defined by this quadratic extension, which is this closed geodesic over the field. And it will be given by the base change of the corresponding phi to this quadratic field capital E, twisted by the same character at the central value. So subconvex bounds for these are important often because they give bounds on periods, and this you will see how we use this in this exact example. It is unfortunate that our theorem's unconditional directly because it should be that I have a strong enough subconvex bound. I don't need the full Lindelof for our theorem to get a power growth. It's just the bound I need is far better than the best subconvex bound known for GL2 forms. I need roughly an exponent of 1/12, and the world record is 1/3 to get something non-trivial, to get an unconditional result. So instead of stating an exponent there, which seems silly, let's just assume I could have even removed Lindelof and just stated Riemann, because that's the main reason these things are true. Okay, but this is an absolutely critical ingredient in our proof. All right, so now I want to explain the tool, which is the basis of making any progress on this. And somehow we want to localize this, localize the problem. And there's something to observe here, which is where we started in this example of Stern. This is our counterexample. If you actually look at the function around the boundary, it doesn't change sign. It's actually only got two signs around the boundary. So this eigenfunction, which is wanting to have very few nodal domains, is doing so because on the boundary, it's just got two signs. And that's something that you can, it's quite common in these kind of situations, as many of you know in cohomology. If you want to create cohomology and the Euler number is 0, then you have trouble. But if you have a fixed point of an involution, then you can sometimes build a cohomology from that by breaking that and going down a dimension. And that's exactly what I'm going to be doing here to try and make nodal domains. And that's the tool for all of this. So let me come back here. So how do we make a topological reduction? So this is a purely elementary theorem in topology of surfaces. Suppose I have a surface X, a fixed set delta of an involution sigma. You think of an isometry as we have there. And suppose that we have a function which is even about this involution. By the way, an eigenfunction which is even about this delta can't be 0 identically. This is the principle of reflection. If you have an eigenfunction which is both even and odd about a geodesic, it's identically 0. So when I talk about the sign changes of phi when restricted to this, there will be sign changes. It can't be identically 0 just by elliptic, there are many, just by the reflection principle. So the topological theorem, which is quite elementary, but there's a miracle that helps us, I want to explain that, is that if n of phi is the number of sign changes of the eigenfunction phi on this delta, I'm looking at an even eigenfunction, then the number of nodal domains is at most n of phi divided by 2 plus 1 minus the genus. So this gives me a tool to produce nodal domains by producing sign changes of phi along this fixed set. The proof is very easy if the nodal set had no self-intersections. If it's non-singular, then a simple induction argument, you have these little blobs, they're symmetric about this, so that if that looks like that, then the other side looks like that, and there you see a nodal domain. If you have another zero here, then they can try interlace, but there's a simple count. And you get a lower bound like this for the guy which is non-singular. That's elementary topology. The miracle here is usually when you are singular, things get bad, but it's a very simple exercise that when you get singular, you only get more nodal domains, not less. So the bad news helps you in this argument, and you just show that this is always a lower bound. So the kind of guy which has a lot of nodal domains is sine x times sine y. Sine nx times sine my on a torus. And it's very singular because it's a checkerboard, and there are many nodal domains, just all the squares. But that's exactly because these things cross and cut out little nodal domains. They don't move around and not touch each other. And I'm saying when they move around and not touch each other, it's much harder to create nodal domains. And in dimension 3, they're probably very hard to make. Okay, so this gives the reduction. And the problem will be from now on to give a lower bound for the number of sign changes of phi on the restriction to this fixed point set of this involution, of this hyperbolic reflection. This is now moving precisely into restriction of phi to a, this is a symmetric space. H is a SO11 sitting in SO21. It's exactly of the type for which we have these period formulae like Walsh-Paget. Well, in this case, exactly Walsh-Paget. Now, getting back to the picture that I painted, but let's look at Gauch's paint. It's a bit nicer. The nodal domains that I'm going to produce this way are only inert, because that lower bound was from the number of sign changes of phi on the restricted to this closed set delta, which is this curve here in this case. And the inert ones are precisely the ones that cross, and it's the ones that cross that I'm creating. So I can only produce inert nodal domains, and that is the reason I'm making progress here, because I've localized it to one dimension. These green ones, I have no idea how to make any of them analytically. And I want to point out that they are most of them. So we're getting a lower bound, but we are limited into what we can do. So it's kind of limited in that sense, because it's not difficult to prove by complexification. This is Zeldich's favorite and everybody's favorite trick. Certainly Bernstein with analytic continuing to a tube domain around the manifold. So there's an upper bound, the number of inert domains, so in a compact segment of the delta, the number of times that inert domains would be the number of times phi changes sign on this boundary. And for that, you can give an upper bound by complexifying the whole story, using this as complex analytic, complexifying the whole story, and then using Jensen's formula to give an upper bound for the number of complex zeros in a tube domain around this. And this is theorem of Toth and Zeldich, and the upper bound is n of phi lambdas at most lambda to the half. So we're producing lambda to the 1/24th nodal domains in all these cases. The maximum we would ever get for these inert nodal domains is lambda to the half. We can't possibly get more. We're nowhere near getting that much. The conjecture from random is that it's a constant times lambda, so most of them are split, and most of them we don't see. And I have no idea how to make those, because they're kind of untouchable. Only the random construction seems to put its finger on them. Otherwise, we might even think those aren't there. All right, so how do we make these sign changes? So now it's going to be the proof is actually not so different to Hardy and Selberg's proof of the number of zeros on the half line for the Riemann zeta function. If any of you have ever looked at that, Hardy proved that the Riemann zeta function has at least t zeros up to high t on the line of half. The way he did it was to compare the integral of phi over a little interval, phi being the C function which changes sign precisely at every 0. And he compared it with the integral of absolute phi. If I show a real valued function has the property that the integral of the function and the integral of the absolute value of the function are not the same, then it changed sign. That's going to be the attack. So how do I get to compare the integral of phi and the integral of absolute of phi? So the first theorem, this is a theorem that was observed by us in our first paper, Ghosh, Reznikov and myself. And that is that the QUE property, and only the QUE property in these compact cases. On the other hand, in the arithmetic case, in the modular group case, we needed quite a bit more complicated arguments because of the cusp. But in the compact case, it's actually just the QUE property of Elon is enough to prove that if you have an even eigenfunction and you restrict to this delta, so I have an L2 eigenfunction on my surface. Lambda is very large. It's a highly oscillating eigenfunction. I restrict phi to this delta. The restriction of phi to delta is not identically 0 because it's even. So it can't be 0, it can't be odd and even at the same time. It's analytic, so it's going to be non-zero. But this says that the L2 norm of the restriction, assuming the L2 norm on the whole space is 1, is uniformly bounded below. That's not completely obvious, though when I end, this is one of the things that Jang and June do much better. They reprove this in a better way. This used the full QUE on the tangent space, not just on the configuration space. So this tells me that the restricted L2 norm, it may grow, but it can't be small. So this notation means independent of lambda, this is bigger than some constant bigger than 0. All right. So if it's odd, there's a similar thing. And in fact, one can make a statement like this, and it's in our paper, that the restriction of phi plus something with the normal derivative of phi scaled with 1 over lambda there is bounded below. The sum of the two squares is greater than or equal to 1. Of course, since we're on this delta where phi is even, so the normal derivative is 0, we just get this lower bound. So that's a starting point. And now to make sign changes, it's very easy. The idea, as I said, was to compare C as a subsegment of this closed geodesic delta. I'm going to compare the integral of phi with the integral of absolute phi. Show they have different size when lambda is large for different segments. So we have a lower bound for the L2 norm. It's less than or equal to the L infinity norm. This is where we'll use Ivanich and my non-subconvex bound. So it's less than the maximum on the whole space, in particular the maximum on delta. That's all I need. Times the integral of absolute phi. And if I break the integral over delta onto the CJs where phi is of constant sign, plus or minus, then n is here the number of sign changes. So I get 1 is less than or equal to the L infinity norm times n times this integral over a sub-segment. The Volt-Bourget formula gives me an upper bound of the square of this in terms of L functions. Unfortunately, I have to use an unconditional theorem here, as I explained a number of times. That is, I have to put in the Lindelof hypothesis to get the best upper bound for the integral of phi. So what Volt-Bourget says to you, if you assume the Lindelof hypothesis, is if you have a little segment of this closed geodesic and you have this highly oscillating phi lambda, you should think of phi lambda as sine lambda, but it's not. It's a function of several variables. But if it's oscillating a lot, you'd expect the integral of phi to go to 0 with lambda, and what this theorem says is it goes at least like lambda to the minus a quarter, and that's completely sharp because Lindelof is sharp and Riemann is sharp. There are no better bounds than that. So this is the best bound you could get from this. And now you can see why sub-convexity is so important, because if I want to get a lower bound for n from this, I better have an upper bound here which is better than lambda to the quarter in order to get a lower bound of n, which gives the bounds are advertised.
Lower bound that you use in the L2 norm, was that, like, you expect that to be sharp?
The lower bound on the L2 norm is absolutely sharp, yeah.
Insert like lambda.
Right, you're going to see something in a second. If you put in a random wave conjecture, you can always try to guess what's going on here by putting in a random wave. Put in the random wave conjecture here, the lower bound is exactly 2. And you'll see that actually you can prove the lower bound of 2. This is the improvement. So I want to spend the last 5 minutes that I have on this unconditional theorem which just does something a little different at the end here and avoids the number theory. It inputs the heavy machine of Lindenstrauss, meaning it will assume the QUE property. Now, to me, it was a bit surprising. Of course, that was the purpose of our proof on this lower bound, is that the QUE property is a very soft property. It's a property about the integral of phi squared, or op a phi lambda phi lambda. It's an integral over the three-dimensional manifold. And now I'm interested in the integral of phi, this restriction to this closed geodesic, on which it might blow up for all I know. And in fact, that was something that we keep on worrying about. However, on hearing about our work, Zeldich said, well, what happens if you integrate by parts, which happened to be a very interesting idea. He constructs a pseudo-differential operator on the manifold, which is a cutoff near the closed geodesic, and with some very careful definition of how the function, the A, is nearby there. And then he takes this op A phi lambda, and he integrates by parts. Integration by parts is always revealing. So he integrates by parts, throwing all the integrals onto the boundary. And as a consequence, he gets that some limit exists. Some complicated limit exists because op A phi lambda converges to the integral of A. That's the only input you have. So we have the sequence for which we have equidistribution, and it's known in these cases. And now we integrate by parts, and we'll get something on the closed geodesic. And this is what, of course, we were doing in a complicated way to get this lower bound of the restriction being bounded below by a universal constant. But this integration by parts picks it up in a much cleaner way and uses the pseudo-differential calculus in a better way than we were doing. And this has been explicated by Zhang. And so their proof is done in any dimension, in any manifold with bicharacteristics. It's a complicated expression. The upshot of their work, of Zeldich and co., was that the restriction to this H, to this closed geodesic, of the phi, some complicated pseudo-differential operators integrated against this, has some limit. But the set of pseudo-differential operators for which you get the information is very limited. For example, it's not obvious and not true from the QUE that the phi lambda, the restriction of the phi lambdas, would be bounded in L2. There's no upper bound. Remember, our theorem is a lower bound for the L2 norm. They explicate this, and this is the exact information that you get from this integration by parts on the QUE input on the closed geodesic, coupled with some bounds on LP bounds on restrictions. So so they're able to localize what we had before. F is any function on the closed geodesic, smooth, fixed, compact support. Well, the closed geodesic, let's assume we're in the compact setting. They're in the compact setting, yeah?
Delta to be a fixed point of involution, or no?
Yeah, absolutely. For this, delta is a closed geodesic, which is a fixed point of the isometry, and phi is even about it.
They use it.
Absolutely. Otherwise, the derivative, I don't know whether phi is small or the derivative of phi. In general, you'll have a sum of two terms there, just like we had. But this is not an inequality. This is an identity. But notice it's not one signed. So it's a difference there. And so this thing, there's no upper bound for this. But the right-hand side is what you get from writing down the QUE on the whole manifold. So this is an integration by parts, which now is something on delta, is telling us something non-trivial about the restriction. In particular, they get a stronger result than we had. We just had this is bigger than a constant, which we didn't specify. And in our proof, we could get that constant. If we worked hard enough, we could see it. But they get it very naturally this way. So not only, so this answers your question. This should be 2. This should converge to 2, the restricted L2 norm. The only thing you get from this is that it's greater than or equal to 2. And that was our starting point. So this doesn't look like it's enough. And that's why I never thought this would by itself be enough. But notice that you do have these integrals, even this, against a lot of test functions. And here they add a very important new idea. They say, well, I don't know what's happening, but let me renormalize these measures by the L2 norm like you do if something's blowing up. Let me rescale it so that it's got L2 norm 1. So they rescale these phi lambdas when restricted to delta, which for all you know blow up You know they can't go to 0. That's an input that's used here. It can only blow up, so you divide by the L2 norm. You multiply by f. You divide by the L2 norm to scale this so that it's not blowing up. And you do what you do in probability theory. You take a weak limit, and you get a measure. And you don't know, and they're all possible different. You don't have a unique limit measure because you're just going through a subsequence. However, remember, we did know the integral against some functions. And the big insight was, let's assume that this function never changes sign on the whole closed geodesic, or some piece of it, which you fix. Then the Fourier transform of that measure will be positive definite. That's a property of positive functions. And what the integrals you have in your hand will be the scaling limit that you get here on the renormalize is this thing here, and you get a measure on the line. You get a distribution on the line, which if the function didn't change sign ever, is positive definite. And then you have enough integrals. So you have some limits. You don't know what your limit is, but you have enough integrals to show your function's not positive definite. So I won't go into that, but that's the final step of the proof. And this last part is a brilliant insight to just say, well, I don't know what's going on. Let me rescale. And the positive definite argument leads to an unconditional theorem. So I think it's a beautiful theorem. It's the first unconditional theorem, and it's like the theorem, the number of nodal domains goes to infinity in an arithmetic situation. But we need this reflection, because otherwise we don't know how to do it. And in higher dimensions, I challenge anybody to make nodal domains, because I think it's very hard, because these sets don't want to close on themselves. So randomly it's extremely difficult to. Practically it seems very difficult to. Of course, if you engineer an eigenfunction, you can do it. But if you're in a chaotic system where the eigenfunctions are given by modular forms, and the whole point is that you can't write them down except say all sorts of things about them indirectly, it is remarkable that they have proved this theorem unconditionally. And thank you for all being here.